For decades, humans have peered into the cosmos, wondering what lies beyond. But our greatest leaps in understanding haven't always come from telescopes. This is the story of our robot explorers, the space probes that have dared to go where we cannot, revealing the secrets of our solar system and beyond. In this video, we'll journey through the history of space probes, from the first tentative steps of the space race to the sophisticated missions of today. We'll examine the key milestones, the groundbreaking discoveries, the engineering challenges, and the future of robotic space exploration. We'll cover probes that orbited, landed, roved, and even impacted celestial bodies. We'll break down this history into distinct eras: the dawn of the space age, lunar exploration, planetary encounters, the outer solar system, comet and asteroid missions, missions to Venus and Mercury, Mars exploration, and the future of space probes. If you're fascinated by space exploration, be sure to subscribe and hit the notification bell so you don't miss future videos like this. Dawn of the space age. The year is 1957. The Cold War is raging, but something extraordinary is about to happen, something that will forever change humanity's perspective, igniting a spark of innovation and pushing us to achieve the impossible. Welcome to the dawn of the space age. For centuries, the stars have captivated us, inspiring myths, legends, and dreams, but until the mid-20th century, they remained frustratingly out of reach. That was about to change, driven by a potent mixture of scientific ambition and geopolitical rivalry. In the aftermath of World War II, both the United States and the Soviet Union recognized the strategic importance of rocketry. Each nation absorbed German rocket technology and recruited key scientists. On the Soviet side, the brilliant but enigmatic Sergei Korolev spearheaded their space program in almost complete secrecy. In America, Wernher von Braun, a former German rocket scientist, became a leading figure in the US efforts. Both were driven by a desire to reach new heights, literally. Then, on October 4th, 1957, the world held its breath. The Soviet Union launched Sputnik 1, the first artificial satellite to orbit the Earth. This wasn't just a scientific achievement, it was a stunning propaganda victory for the Soviets, demonstrating their technological prowess and sparking what became known as the Sputnik crisis in the United States. Sputnik was a simple aluminum sphere, but its beeping signal echoing across the globe symbolized a new era. The reaction in America was a mixture of awe and alarm. Newspapers screamed headlines about a space gap. People questioned America's technological superiority. Schools introduced new science and math programs, all in an effort to catch up with the Soviets. The space race was officially on. Just a month later, in November 1957, the Soviets launched Sputnik 2, carrying a small dog named Laika. While this demonstrated the possibility of sending living organisms into space, it also highlighted the ethical dilemmas involved. Laika's mission was a one-way trip, and her sacrifice sparked debate about the cost of progress. The United States, meanwhile, struggled to keep pace. Early attempts to launch satellites were plagued by spectacular failures, often played out live on television. The Vanguard rocket, intended to be America's answer to Sputnik, exploded on the launch pad in a humiliating display, but America learned from its mistakes. On January 31st, 1958, the US successfully launched Explorer 1. This satellite carried instruments that detected the Van Allen radiation belts, zones of energetic particles surrounding the Earth, a major scientific discovery. Recognizing the need for a unified and focused space program, President Dwight D. Eisenhower signed the National Aeronautics and Space Act in July 1958, creating NASA. This marked a turning point, consolidating existing space efforts and providing the resources and leadership necessary to compete with the Soviets. The focus shifted towards putting a human in space. Both the United States and the Soviet Union began intensive programs to select and train their first astronauts, pushing the limits of human endurance and engineering. The US Mercury program aimed for simple one-man missions, while the Soviets were more ambitious. On April 12, 1961, the Soviet Union achieved another monumental milestone. Yuri Gagarin became the first human in space, orbiting the Earth once in his Vostok 1 spacecraft. His flight lasted just over 100 minutes, but it captured the imagination of the world and solidified the Soviet Union's lead in the space race. Just weeks later, on May 5, 1961, Alan Shepard became the first American in space, though his suborbital flight was shorter than Gagarin's orbit. While it wasn't a first, it proved that the United States was quickly catching up. Then, on February 20, 1962, John Glenn became the first American to orbit the Earth, completing 3 orbits in his Friendship 7 capsule. This was a pivotal moment for NASA, restoring confidence in the American space program and inspiring a new generation of scientists and engineers. The early 1960s saw a flurry of activity in space. Valentina Tereshkova became the first woman in space in 1963. Alexei Leonov performed the first spacewalk in 1965. Each mission pushed the boundaries of human exploration and technological innovation. But the ultimate goal was clear. In 1961, President John F. Kennedy challenged the nation to land a man on the moon and return him safely to Earth before the end of the decade. This audacious goal galvanized the nation and set the stage for the next chapter of the space age: lunar exploration. From the moment humans first gazed upon the moon, our curiosity was ignited. A celestial body of mystery, beauty, and wonder, the moon has been an irresistible lure for scientists and dreamers alike. In the 1960s and 1970s, humanity embarked on a thrilling journey to explore and understand our lunar neighbor. This is the story of those lunar pioneers. The space race between the United States and the Soviet Union reached its zenith during the 1960s. Both nations recognized the immense scientific potential of the moon and the propaganda value of being the first to explore it. The stage was set for a series of groundbreaking missions that would reshape our understanding of the cosmos. The Soviet Union struck first with Luna 1, the first spacecraft to reach the vicinity of the moon. Though it missed its intended target, Luna 1 provided invaluable data on the lunar environment and demonstrated the feasibility of lunar missions. Not to be outdone, the United States countered with Pioneer 4. Though it, too, missed the moon, Pioneer 4 gathered crucial data on the radiation belts surrounding Earth, paving the way for future lunar missions. The Soviet Union reclaimed the lead with Luna 2, the first spacecraft to make contact with the lunar surface. Luna 2 carried a collection of Soviet symbols, including the Soviet coat of arms, symbolizing the nation's triumph in the early stages of the space race. The United States sought to catch up with the Soviet Union through the Ranger program, a series of missions designed to obtain high-resolution images of the lunar surface. Though the first 6 Ranger missions ended in failure, Rangers 7, 8, and 9 were resounding successes, beaming back thousands of images and providing valuable insights into the moon's geology. Not to be outdone, the Soviet Union achieved another historic first with Luna 3, which photographed the far side of the moon on October 7, 1959. This accomplishment provided the first glimpse of the mysterious unseen face of the moon and further fueled the world's fascination with lunar exploration. The United States continued its lunar exploration efforts with the Surveyor program. These 7 missions, launched between 1966 and 1968, obtained high-resolution images of the lunar surface, performed lunar soil analyses, and tested the feasibility of soft landings. The Surveyor program laid the groundwork for the Apollo missions, which would ultimately bring humans to the moon. The Soviet Union, meanwhile, was not idle. Luna 9 achieved the first successful soft landing on the moon on February 3, 1966, and returned the first panoramic images of the lunar surface. This accomplishment marked a significant milestone in the history of lunar exploration. the Soviet Union continued to push the boundaries of lunar exploration with Luna 16, which performed the first robotic sample return mission from the Moon on September 20th, 1970. This mission collected 101 grams of lunar soil, providing scientists with a wealth of new data on the Moon's composition and history. The United States, however, would ultimately claim the greatest prize in the race to the Moon. The Apollo program, a monumental endeavor involving more than 400,000 people, culminated in the historic moon landing of Apollo 11 on July 20th, 1969. Neil, the Soviet Union's Luna 24 mission, launched on August 9, 1976, marked the final chapter in the era of lunar exploration probes. Luna 24 performed the final Soviet sample return mission from the Moon, collecting 170.1 grams of lunar soil and providing a fitting coda to this remarkable period of exploration. The Apollo program. One small step for man, one giant leap for mankind. Words that echo through history, forever linked to the Apollo program. But Apollo was more than just a few steps on the Moon. It was a monumental undertaking, a triumph of human ingenuity, and a defining moment of the 20th century. In this video, we'll explore the incredible story of Apollo. The Apollo program wasn't just about reaching the Moon. It was about proving that seemingly impossible goals can be achieved when you have the drive and the will to do so. President John F. Kennedy recognized the importance of space exploration, not only for national security, but also for national pride. In 1961, just weeks after Yuri Gagarin became the first human in space, Kennedy issued a bold challenge to the nation and said, "I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the Moon and returning him safely to the Earth." It was an audacious goal, given the technology of the time, but Kennedy's vision ignited the imagination of the American public and set the stage for the Apollo program. Before Apollo could reach for the Moon, NASA needed to learn how to put humans into space and keep them alive. This was the purpose of Projects Mercury and Gemini. Project Mercury focused on achieving basic human spaceflight. 6 American astronauts, the Mercury 7, paved the way, proving that humans could survive and function in the harsh environment of space. Project Gemini built on the successes of Mercury, focusing on developing the technologies and techniques necessary for lunar missions. Gemini astronauts performed spacewalks, practiced rendezvous and docking, and conducted experiments to understand the long-duration effects of spaceflight. These 2 programs were critical stepping stones, providing the foundation of experience and expertise that would make Apollo possible. The Apollo program demanded a new generation of spacecraft and rockets. The centerpiece of the program was the Saturn V rocket, a colossal machine that remains the most powerful rocket ever built. Standing over 360 feet tall, the Saturn V generated an incredible 7.6 million pounds of thrust at liftoff. It was a marvel of engineering, capable of carrying the Apollo spacecraft to the Moon. The Apollo spacecraft consisted of 3 main components: the command module, where the astronauts lived during the mission; the service module, which housed the life support systems and propulsion; and the lunar module, or LM, the spider-like vehicle that would carry 2 astronauts to the lunar surface. Each component was meticulously designed and tested, pushing the boundaries of engineering and technology. The Apollo program was not without its setbacks. On January 27, 1967, tragedy struck during a launch rehearsal test for Apollo 1. A fire erupted inside the command module, killing astronauts Gus Grissom, Ed White, and Roger Chaffee. The Apollo 1 disaster was a devastating blow to NASA and the nation. It forced a complete redesign of the command module, focusing on fire safety and emergency procedures. The loss of the Apollo 1 crew served as a somber reminder of the inherent risks of space exploration, but it also strengthened the resolve of the program to succeed. After the Apollo 1 tragedy, NASA worked tirelessly to improve safety and reliability. In December 1968, Apollo 8 became the first manned spacecraft to orbit the Moon. Astronauts Frank Borman, Jim Lovell, and Bill Anders circled the Moon 10 times, sending back stunning images of the lunar surface. But perhaps the most iconic image from Apollo 8 was Earthrise, a breathtaking view of our planet rising above the lunar horizon. This image captured the fragility and beauty of Earth and helped to galvanize support for the space program. As they orbited the Moon on Christmas Eve, the astronauts read from the Book of Genesis in a live broadcast that was heard by millions around the world. In July 1969, the world watched with bated breath as Apollo 11 embarked on its journey to the Moon. On July 20th, the lunar module, nicknamed Eagle, separated from the command module and began its descent. With only seconds of fuel remaining, Neil Armstrong piloted the Eagle to a safe landing in the Sea of Tranquility. 6 hours later, Neil Armstrong became the first human to set foot on the Moon. Buzz Aldrin soon joined him, and the two astronauts spent over 2 hours exploring the lunar surface. They collected samples of rocks and soil, conducted experiments, and planted an American flag. Apollo 11 was a monumental achievement, a testament to human ingenuity and a symbol of American leadership. Following the success of Apollo 11, NASA continued to explore the Moon with 6 more landing missions. Apollo 12 explored Oceanus Procellarum. Apollo 14 explored the Fra Mauro Highlands. Apollo 15 explored the Hadley-Apennine region, using the first lunar roving vehicle. Apollo 16 explored the Descartes Highlands, and Apollo 17 was the final mission, with geologist Harrison Schmitt on board. These missions yielded a wealth of scientific data, revealing the Moon's composition, history, and relationship to the Earth. Astronauts deployed scientific instruments, collected hundreds of kilograms of lunar rocks and soil, and left footprints that will likely remain undisturbed for millions of years. Not all Apollo missions went according to plan. Apollo 13, launched in April 1970, faced a life-threatening crisis when an oxygen tank exploded in the service module. The explosion crippled the spacecraft, leaving the crew with limited power, oxygen, and water. Through the ingenuity of the astronauts and the dedication of the mission control team, an Apollo 13 limped back to Earth, using the lunar module as a lifeboat. The safe return of Apollo 13 was a triumph of human resilience and problem-solving under extreme pressure. Despite its successes, the Apollo program was cut short, public interest waned, funding was reduced, and the focus shifted to other priorities. Apollo 17, launched in December 1972, was the final mission to the Moon. The program was formally cancelled soon after. While the reasons were complex, it was clear that the nation had lost some of its initial enthusiasm for lunar exploration. The Apollo program may have ended, but its legacy continues to inspire. Apollo spurred countless technological innovations, from computer technology and materials science to medical equipment and consumer products. The program also fostered a generation of scientists, engineers, and innovators who shaped the world we live in today. Most importantly, Apollo demonstrated the power of human ambition and the potential for achieving the seemingly impossible. It inspired people around the world to dream big, to push boundaries, and to strive for a better future. Planetary encounters. Ever wonder how we first truly saw the other planets in our solar system? Before the Hubble telescope, before fancy rovers, it was all about the probes. These robotic pioneers, hurled into the void, gave us our first close-up glimpses of worlds beyond our own. From the 1960s to the 1980s, humanity embarked on a thrilling journey to explore the planets of our solar system. Through a series of ambitious space probe missions, we uncovered new insights and unraveled the mysteries of these celestial bodies. In the early days of space exploration, our attention was focused on the inner planets: Mercury, Venus, Earth, Mars, and Jupiter. The first successful interplanetary space probe was NASA's Mariner 2, which launched in August 1962. Its primary mission was to conduct close observations of Venus and transmit data back to Earth. On December 14, 1962, Mariner 2 made history as it became the first spacecraft to encounter another planet. It provided valuable information about Venus's dense atmosphere, extreme temperatures, and lack of a magnetic field. Following the success of Mariner 2, NASA launched Mariner 4 in November 1964 with the goal of surveying Mars. This mission marked the first time a spacecraft had ever visited the Red Planet. On July 14, 1965, Mariner 4 made its closest approach to Mars, capturing the first ever images of another planet from space. These 21 photographs revealed a heavily cratered surface, similar to Earth's moon. Meanwhile, the Soviet Union was also making great strides in space exploration. In August 1970, the Venera 7 mission successfully landed on Venus, becoming the first spacecraft to make a soft landing on another planet. Venera 7 transmitted data for 23 minutes, providing valuable insights into Venus's harsh surface conditions, including extreme temperatures and pressures. In March 1972, NASA's Pioneer 10 mission was launched, with the objective of exploring the outer planets. This marked the beginning of a new era in space exploration, as humanity prepared to venture further into the cosmos. On December 3, 1973, Pioneer 10 made its historic encounter with Jupiter, capturing stunning images and collecting invaluable data about the gas giant's atmosphere, magnetosphere, and moons. This mission paved the way for future explorations of the outer planets. In October 1981, the Soviet Union's Venera 13 mission successfully landed on Venus and transmitted color panoramic images of the planet's surface. This mission also conducted experiments to analyze Venus's soil composition and atmospheric conditions. These are just a few of the many space probe missions that transformed our understanding of the solar system during the 1960s, 1970s, and 1980s. As we continue to push the boundaries of space exploration, we can look back on these early missions with a sense of pride and awe, knowing that they laid the foundation for our ongoing journey into the cosmos. The outer solar system. For centuries, the outer solar system was a realm of mystery, a distant frontier only glimpsed through telescopes. But in the late 20th and early 21st centuries, humanity sent its robotic emissaries to explore these icy giants and their captivating worlds. These groundbreaking revolutionized our understanding of Jupiter, Saturn, Uranus, Neptune, and beyond. We'll delve into the incredible discoveries made by Voyager, Galileo, Cassini-Huygens, and New Horizons, revealing the secrets of these distant realms. The 1970s were a golden age for space exploration, and the Voyager program was a shining example. Launched in 1977, Voyager 1 and 2 embarked on a grand tour of the outer planets, taking advantage of a rare alignment that occurs only once every 176 years. Voyager 1 focused primarily on Jupiter and Saturn, while Voyager 2 continued on to Uranus and Neptune. The data they sent back was astonishing. At Jupiter, Voyager revealed the complexity of the planet's atmosphere, the sheer size and ferocity of the Great Red Spot, and the surprising volcanic activity on its moon Io. Before Voyager, Io was thought to be a cold, dead world. Instead, it was found to be the most volcanically active object in the solar system, constantly spewing sulfurous material into space. Voyager also discovered that Jupiter has a faint ring system and provided detailed images of Europa, Ganymede, and Callisto, hinting at the possibility of subsurface oceans beneath their icy crusts. At Saturn, Voyager revealed the intricate beauty of its rings, showing them to be composed of countless icy particles ranging in size from dust grains to small houses. The probes also discovered several new moons and provided our first close-up views of Titan, Saturn's largest moon. Titan's thick, hazy atmosphere obscured its surface, but Voyager's instruments detected the presence of organic molecules, fueling speculation about the possibility of prebiotic chemistry. Voyager 2's encounters with Uranus and Neptune were equally groundbreaking, providing our first and only close-up views of these ice giants. At Uranus, Voyager discovered a highly tilted magnetic field and revealed a surprisingly featureless atmosphere. At Neptune, Voyager discovered the Great Dark Spot, a storm system similar to Jupiter's Great Red Spot, and revealed the presence of active geysers on its moon Triton. The Voyager missions transformed our understanding of the outer solar system, proving that these distant worlds were far more dynamic and complex than previously imagined. These probes continue to travel outward, sending back data about the interstellar medium as they journey towards the edge of our solar system. While Voyager provided a fleeting glimpse of the outer planets, the Galileo mission, launched in 1989, offered a more in-depth study of Jupiter and its moons. Galileo spent 8 years orbiting Jupiter, providing a wealth of data about the planet's atmosphere, magnetic field, and the intriguing characteristics of its Galilean moons. One of Galileo's most significant achievements was the deployment of an atmospheric probe into Jupiter's atmosphere. The probe transmitted data for nearly an hour before being crushed by the immense pressure, providing valuable insights into the planet's composition and weather patterns. Galileo also provided compelling evidence for the existence of subsurface oceans on Europa, Ganymede, and Callisto. By measuring the gravitational effects of these moons on the spacecraft, Galileo scientists were able to infer the presence of liquid water beneath their icy surfaces. The discovery of these potential oceans has profound implications for the search for life beyond Earth, as liquid water is considered a key ingredient for life as we know it. Galileo also witnessed the impact of Comet Shoemaker-Levy 9 into Jupiter in 1994, providing a unique opportunity to study the effects of a large impact on a planetary atmosphere. Following in the footsteps of Voyager, the Cassini-Huygens mission arrived at Saturn in 2004, embarking on a 13-year exploration of the planet, its rings, and its moons. Cassini was an orbiter, while Huygens was a probe designed to land on Titan. The Huygens probe successfully landed on Titan in 2005, becoming the first spacecraft to land on a moon in the outer solar system. Huygens transmitted data and images for over an hour, revealing a bizarre landscape of methane rivers, lakes, and rain. Cassini's observations revealed that Titan's atmosphere is primarily composed of nitrogen, with traces of methane and other organic molecules. The surface temperature is extremely cold, around -179 degrees Celsius, -290 degrees Fahrenheit, but the presence of liquid methane suggests a hydrological cycle similar to Earth's water cycle. Cassini also provided stunning images of Saturn's rings, revealing their complex structure and composition in unprecedented detail. The spacecraft discovered several new moons embedded within the rings and observed the dynamic interactions between the rings and these small moons. One of Cassini's most surprising discoveries was the presence of geysers erupting from the south pole of Enceladus, another of Saturn's moons. These geysers were found to be spewing water ice, organic molecules, and salts into space, indicating the presence of a subsurface ocean beneath Enceladus's icy crust. The discovery of a potentially habitable ocean on Enceladus, along with the lakes and rivers on Titan, made Saturn's system a prime target in the search for extraterrestrial life. While not one of the gas giants, Pluto was considered a planet until 2006. The New Horizons mission, launched in 2006, finally provided humanity with its first close-up view of this distant world. New Horizons flew past Pluto in 2015, revealing a surprisingly complex and geologically active world. The spacecraft captured stunning images of Pluto's heart-shaped glacier, known as Sputnik Planitia, and discovered evidence of mountains, valleys, and canyons on its surface. New Horizons also revealed that Pluto has a thin atmosphere of nitrogen, methane, and carbon monoxide, and that its largest moon, Charon, also displays evidence of past geological activity. After its flyby of Pluto, New Horizons continued its journey into the Kuiper Belt, a region of icy bodies beyond Neptune. In 2019, New Horizons flew past Arrokoth, a Kuiper Belt object, providing our first close-up view of a primordial building block of the solar system. The New Horizons mission demonstrated that these distant regions are far more dynamic and diverse than previously imagined. Comet and asteroid missions. But getting close enough to unlock those secrets, that's been a journey of incredible ingenuity, daring missions, and mind-blowing discoveries. The 1980s marked a turning point. Halley's Comet, a returning visitor every 75 to 76 years, presented a rare, can't-miss opportunity. The world raced to meet it. The Soviet Union sent 2 Vega probes, Vega 1 and Vega 2, in 1986, both returning valuable images and data about the comet's nucleus and coma. Their data helped other missions navigate more accurately. Japan also joined the fray with Sakigake and Suisei. Sakigake was more of a technology demonstrator, but Suisei focused on studying the comet's hydrogen corona. But Europe truly stole the show with Giotto. The European Space Agency's probe daringly flew within 600 kilometers of Halley's nucleus, sending back the first ever close-up images of a comet's dark, icy core. This was a huge technological feat, and a revelation for scientists who had previously only seen comets from afar. The information collected helped refine our understanding of cometary composition, a dirty snowball of ice, dust, and organic molecules. These missions laid the groundwork for future comet encounters. The late 1990s and early 2000s saw a shift in focus, not just observation, but interaction and sample return. NASA's Deep Space 1, launched in 1998, was a technology demonstrator showcasing ion propulsion, a highly efficient but low-thrust system. It successfully flew by the asteroid 9969 Braille and the comet 19P/Borrelly, proving the viability of this new propulsion system for deep space missions. But the real game-changer was Stardust. Launched in 1999, Stardust journeyed to comet 81P/Wild 2, where it used a unique aerogel collector to capture dust particles from the comet's coma. In 2006, the Stardust sample return capsule parachuted back to Earth, carrying pristine cometary material. This was the first time scientists had directly analyzed a comet sample in terrestrial labs. The analysis of these particles provided invaluable insights into the building blocks of our solar system and the potential for comets to deliver prebiotic molecules to Earth. The European Space Agency once again pushed the boundaries of space exploration with the Rosetta mission. Launched in 2004, Rosetta spent 10 years traveling to comet 67P/Churyumov-Gerasimenko. Rosetta didn't just fly by. It orbited the comet for over 2 years, providing unprecedented detailed observations of its activity as it approached and moved away from the Sun. But the most audacious part of the mission was the deployment of the Philae lander. On November 12, 2014, Philae separated from Rosetta and descended towards the comet's surface. The landing didn't go exactly as planned. Harpoons designed to anchor Philae failed to fire, causing it to bounce across the surface before coming to rest in a shadowed area. Despite the less than ideal landing site, Philae managed to conduct a series of experiments, transmitting valuable data about the comet's composition before its batteries ran out. Rosetta continued to observe the comet until September 2016, when it deliberately crash-landed on its surface, ending a historic mission. Rosetta and Philae provided a wealth of information about cometary structure, composition, and activity, showing us that comets are much more complex and dynamic than previously thought. While comets captured the early spotlight, asteroids were quietly becoming a focus of increasing interest. These rocky bodies, concentrated mainly in the asteroid belt between Mars and Jupiter, offer another window into the solar system's formation. NASA's NEAR Shoemaker became the first spacecraft to orbit an asteroid, 433 Eros, in 2000. NEAR mapped the asteroid's surface in detail and even landed, unexpectedly but successfully, on it in 2001. While NEAR didn't collect samples, the Japanese space agency JAXA took the next leap with the Hayabusa mission. Hayabusa targeted the small peanut-shaped asteroid 25143 Itokawa. The mission was plagued with technical problems, including a failed landing and sample collection attempt. Despite these challenges, Hayabusa managed to collect a tiny amount of surface material and, against all odds, returned it to Earth in 2010. Even a few grains of asteroid dust proved immensely valuable, providing insights into the asteroid's mineralogy and history. Hayabusa demonstrated the feasibility of asteroid sample return, paving the way for future missions. The successes of Hayabusa spurred a new generation of asteroid missions. JAXA's Hayabusa 2 visited the carbonaceous asteroid 162173 Ryugu. It deployed multiple rovers onto the surface and even created an artificial impact crater to collect subsurface material. In 2020, Hayabusa 2 successfully returned its samples to Earth. NASA's OSIRIS-REx mission targeted the near-Earth asteroid 101955 Bennu, a carbon-rich asteroid that may contain organic molecules. OSIRIS-REx successfully collected a sample from Bennu in 2020 and is on its way back to Earth, scheduled to arrive in 2023. Both Hayabusa 2 and OSIRIS-REx are providing unprecedented insights into the composition and evolution of asteroids, helping us understand the early solar system and the potential for asteroids to deliver water and organic molecules to Earth. Looking to the future, NASA's Lucy mission, launched in 2021, is embarking on a grand tour of the Trojan asteroids, two groups of asteroids that share Jupiter's orbit. Lucy will visit multiple Trojan asteroids, providing valuable information about the diversity of these ancient bodies. Even more ambitious is NASA's Psyche mission. Psyche is targeting a unique metal asteroid of the same name, believed to be the exposed core of a protoplanet. Studying Psyche could provide unprecedented insights into the formation of planetary cores. Beyond scientific exploration, there's growing interest in the potential of asteroid mining. Asteroids contain valuable resources, including water, precious metals, and rare earth elements. While asteroid mining is still in its early stages, several companies are developing technologies for extracting resources from asteroids. The potential benefits are enormous, ranging from providing resources for space exploration to alleviating resource scarcity on Earth. From the pioneering missions to Halley's Comet to the bold ambitions of asteroid mining, the exploration of comets and asteroids has been a remarkable journey of scientific discovery and technological innovation. These missions are not just about exploring space. They're about understanding our origins, our place in the universe, and our potential future among the stars. Missions to Venus and Mercury. While Mars often steals the spotlight, the inner worlds of Venus and Mercury hold incredible secrets and present some serious challenges to space exploration. For decades, scientists have braved scorching temperatures, crushing pressures, and bizarre landscapes to understand these enigmatic planets. In 1974 and 1975, Mariner 10 made 3 flybys of Mercury, mapping about 45% of its surface. What it revealed was a heavily cratered world, similar to our Moon, but with unique features like giant scarps, huge cliffs stretching for hundreds of kilometers. These scarps suggest that Mercury's core cooled and contracted early in its history, causing the surface to wrinkle and crack. Mariner 10 also gave us a glimpse of Venus, though it was primarily a flyby. It revealed a thick, cloudy atmosphere composed mainly of carbon dioxide, hiding the surface below. It confirmed the planet's extremely high surface temperature, hot enough to melt lead. While Mariner 10 gave us flyby data, the Soviet Union was determined to actually land on Venus. Their Venera program was one of the most ambitious and arguably insane endeavors in space exploration history. Venus is a brutal environment. The surface temperature is around 900 degrees Fahrenheit, hotter than an oven's self-cleaning cycle, and the atmospheric pressure is 90 times that of Earth at sea level, equivalent to being almost a kilometer underwater. The Venera landers were built like tanks, designed to withstand these extreme conditions for as long as possible, and some of them did succeed. Venera 9 and 10 managed to transmit the first images from the surface of another planet back to Earth in 1975. These grainy black and white images showed a rocky, desolate landscape bathed in an orange glow. Subsequent Venera missions, like Venera 13 and 14, even managed to capture color images and analyze soil samples, giving us invaluable insights into Venus's geology. These missions were engineering marvels, pushing the limits of what was possible at the time. After the intense activity of the 1970s and early 80s, exploration of Venus and Mercury slowed. Focus shifted to other targets, like Mars and the outer planets. However, interest in these inner worlds never completely disappeared, and new technologies were being developed that would eventually lead to a renaissance in Venus and Mercury exploration. One key development was improved radar technology, which allowed us to peer through Venus's thick clouds and map its surface from orbit. The Magellan mission, launched by NASA in 1989, used radar to create detailed maps of 98% of Venus's surface, revealing a world of vast plains, towering volcanoes, and intriguing geological features. In the 21st century, we've seen a resurgence of missions to both Venus and Mercury. The first major mission to Mercury in over 30 years was NASA's Messenger spacecraft, launched in 2004. Messenger entered orbit around Mercury in 2011 and spent 4 years studying the planet in unprecedented detail. Images of the Messenger spacecraft in flight, artists' renderings of it orbiting Mercury, and stunning images of Mercury from Messenger. Messenger revealed a wealth of new information about Mercury. It confirmed the presence of water ice in permanently shadowed craters near the poles, despite the planet's proximity to the Sun. It also discovered that Mercury's magnetic field is offset from the planet's center, a unique characteristic in our solar system. And perhaps most surprisingly, it found evidence of organic compounds on Mercury's surface. Close-up images of Mercury's polar craters, diagrams showing the offset magnetic field, and images showing possible organic compounds. Messenger's mission ended in 2015 when it deliberately crashed into Mercury's surface, creating a new crater and providing a final bit of scientific data. Currently en route to Mercury is the Bepi-Colombo mission, a joint project between the European Space Agency, ESA, and the Japan Aerospace Exploration Agency, JAXA. Launched in 2018, Bepi-Colombo is scheduled to enter orbit around Mercury in 2025. Images and animations of the Bepi-Colombo spacecraft, diagrams of its complex trajectory, and simulations of the two orbiters exploring Mercury. Bepi-Colombo consists of two separate orbiters, the Mercury Planetary Orbiter, MPO, and the Mercury Magnetospheric Orbiter, MMO. These orbiters will work together to study Mercury's surface, interior, and magnetic environment in even greater detail than Messenger. The mission aims to answer fundamental questions about Mercury's formation, evolution, and its unusual characteristics. And what about Venus? After decades of relative neglect, Venus is finally experiencing a major comeback. NASA and ESA have recently selected 3 ambitious missions to explore Venus in the coming years: Da Vinci, Veritas, and Envision. Da Vinci is a descent probe that will plunge through Venus's atmosphere, measuring its composition and structure as it falls. It will also capture stunning images of the surface during its descent, providing a close-up look at Venus's geology. Veritas is an orbiter that will use radar to create high-resolution maps of Venus's surface, searching for evidence of active volcanism and plate tectonics. It will also measure Venus's gravity field to understand its internal structure. ESA's Envision mission will also orbit Venus, complementing Veritas with its own radar instrument and a suite of spectrometers to study Venus's surface composition and atmosphere. Together, these three missions promise to revolutionize our understanding of Venus and its evolution. So, why are we investing so much time and resources into exploring these scorching worlds? Well, Venus and Mercury hold clues to fundamental questions about planetary formation and evolution. Venus, in particular, is a cautionary tale. It's believed that Venus may have once been a much more Earth-like planet, with liquid water oceans. Understanding why Venus became the hellish world it is today could help us protect our own planet from a similar fate. Could it have been a runaway greenhouse effect? Mercury, on the other hand, provides insights into the formation and evolution of planetary cores and magnetic fields. Its unusually large iron core and its unique magnetic field continue to puzzle scientists. Exploring these extreme environments pushes the boundaries of our technology and inspires us to ask big questions about our place in the universe. The missions of the 1970s laid the foundation, and the modern missions are building on that legacy in incredible ways. Mars exploration. Before we had rovers the size of cars trundling across the Martian surface, we had Pathfinder. Launched in 1996 and landing in 1997, Pathfinder, with its tiny rover Sojourner, was a game-changer. Pathfinder wasn't just about getting to Mars. It was about getting there cheaply and demonstrating a new way to land. It used airbags to cushion its fall, a revolutionary approach that significantly reduced the mission's cost and complexity. And Sojourner, this little six-wheeled rover, roughly the size of a microwave, became a global sensation. Sojourner, despite its limitations, proved that we could successfully operate a mobile robot on Mars. It gathered data on the Martian atmosphere, soil composition, and took heaps of photos, sending back a wealth of information about the Ares Vallis region. Pathfinder proved that low-cost, high-impact missions to Mars were possible, paving the way for even more ambitious endeavors. Following Pathfinder's success, NASA launched the Mars exploration rovers Spirit and Opportunity in 2003. These rovers were larger, more capable, and packed with scientific instruments designed to do one thing in particular: find evidence of past water activity. Spirit landed in Gusev crater, believed to have once been a lake bed, while Opportunity touched down in Meridiani Planum, a region rich in hematite, a mineral that often forms in the presence of water. And they delivered. Opportunity famously found evidence of ancient acidic water at Meridiani Planum, confirming that Mars was once a much wetter place. Spirit, despite getting stuck in soft soil later in its mission, also uncovered evidence of hydrothermal activity in Gusev crater, suggesting that Mars may have once had conditions suitable for microbial life. These rovers far exceeded their initial 90-day mission timelines. Spirit operated for over 6 years, while Opportunity became an absolute legend, exploring Mars for nearly 15 years. Their discoveries revolutionized our understanding of Martian geology and the planet's potential for past habitability. Sadly, Opportunity was lost in 2018 due to a massive dust storm that blocked sunlight from reaching its solar panels. Next up, we have Curiosity, a nuclear-powered rover the size of a small car. Launched in 2011 and landing in 2012, Curiosity was sent to Gale Crater, a massive impact crater containing a towering mountain of layered sediments, Mount Sharp. Its mission, to assess whether Gale Crater ever had an environment capable of supporting microbial life. Curiosity is a mobile science lab on wheels. It has a suite of sophisticated instruments, including a laser to vaporize rocks and analyze their composition, a drill to collect samples from beneath the surface, and a miniature chemistry lab to identify organic molecules. And it has been making some groundbreaking discoveries. Curiosity has found evidence of an ancient freshwater lake within Gale Crater, confirming that the area was habitable billions of years ago. It has also detected organic molecules, the building blocks of life, in Martian rocks, although it's important to note that these molecules could also have formed through non-biological processes. Curiosity is still exploring Gale Crater today, climbing Mount Sharp and continuing to unravel the history of this fascinating region. Its findings have dramatically strengthened the case for past habitability on Mars, and it continues to provide invaluable data for future missions. Which brings us to the present and the Perseverance rover, which landed in Jezero Crater in 2021. Jezero Crater is believed to have once been a lake fed by a river, making it a prime location to search for signs of past life. Perseverance has two primary goals: to search for biosignatures, potential evidence of past life, and to collect rock and soil samples that will eventually be returned to Earth for detailed analysis. This is a huge deal. Perseverance is equipped with even more advanced instruments than Curiosity, including MOXIE, a device that is successfully producing oxygen from the Martian atmosphere. This technology could be crucial for future human missions to Mars, providing both breathable air and rocket propellant. Alongside Perseverance is Ingenuity, the Mars helicopter, which has become the first aircraft to achieve powered, controlled flight on another planet. Ingenuity is revolutionizing how we explore Mars by providing an aerial perspective and scouting locations for Perseverance. Together, Perseverance and Ingenuity are pushing the boundaries of Martian exploration and paving the way for future robotic and, eventually, human missions. And what does the future hold? Scientists are constantly analyzing data from these missions and planning future surface and orbital missions to gain a great understanding of the red planet. The ultimate goal is to determine whether life ever existed on Mars, and ultimately, to prepare for human exploration. The exploration of Mars isn't just about science. It's about answering some of the biggest questions humanity has ever asked. Are we alone in the universe? What is the origin of life? And what is our destiny as a species? Mars, with its potential for past habitability, offers a unique opportunity to address these fundamental questions. By studying Mars, we can learn more about the conditions necessary for life to arise and evolve, and gain a better understanding of our own planet. The journey is far from over. There are still so many mysteries waiting to be uncovered on Mars, and with each new mission, each new discovery, we get one step closer to unlocking the secrets of the red planet and our place in the cosmos. Current and ongoing missions. Exploring our solar system helps us answer some of the most fundamental questions about our place in the universe. It helps us understand the origins of life. Could life exist elsewhere? By studying other planets, especially those that might have once been habitable, we can learn about the conditions necessary for life to arise, the formation of our solar system. Each planet is a time capsule, preserving clues about the solar system's early history. The future of Earth. By understanding how other planets have changed over time, we can gain insights into our own planet's climate and potentially mitigate future environmental challenges. Advancing technology. Planetary missions drive innovation in robotics, materials science, and communication, pushing the boundaries of what's possible. Our first stop is the gas giant, Jupiter, and its dedicated explorer, Juno. Launched in 2011 and arriving in 2016, Juno isn't just orbiting Jupiter, it's getting up close and personal with the planet like never before. Juno's mission is to peel back the layers of Jupiter and understand what lies beneath those swirling clouds. Specifically, Juno aims to determine the composition of Jupiter. Is there a solid core? What's the distribution of heavy elements? map Jupiter's intense magnetic and gravitational fields. This reveals information about the planet's internal structure and dynamics. Explore Jupiter's magnetosphere. How does it interact with the solar wind, and how does it generate auroras that are far more powerful than Earth's? To achieve these goals, Juno is packed with state-of-the-art scientific instruments. Microwave radiometer, MWR. This instrument peers deep into Jupiter's atmosphere to measure the amount of water and ammonia. Magnetometer, MAG. Maps. Jupiter's powerful magnetic field, revealing secrets about the planet's interior. Gravity science, gravity. Maps the Jovian mass and density which helps determine the planet's atmospheric composition. Jovian, infrared auroral mapper, GIRAM. GIRAM captures infrared light emitted from Jupiter, giving us an inside look into the planet's composition and temperature. Ultraviolet spectrometer, UVS. This instrument observes the far ultraviolet emissions from Jupiter's magnetosphere. JunoCam. This camera captures visible light images of Jupiter's cloud tops. Although it's not a scientific instrument, the images from JunoCam provide awesome visuals. And what has Juno found? Prepare to be amazed. Juno has revealed a highly complex and dynamic atmosphere, with giant cyclones swirling around Jupiter's poles. These cyclones are unlike anything seen on Earth. Its magnetic field measurements have shown that Jupiter's magnetic field is more complex and irregular than previously thought. There's a great blue spot near the equator, an area of intense magnetic flux. Juno's gravity measurements suggest that Jupiter's core may be larger and less dense than previously expected. It might even be fuzzy, meaning it's not a distinct solid core, but rather a gradual mixture of heavy elements. It also Jupiter's auroras, which are the most powerful in the solar system. They're created by particles accelerated along magnetic field lines. Juno's mission has been extended, and it will continue to orbit Jupiter, gathering even more data. This includes studying the planet's faint rings and exploring the volcanic moon Io during close flybys. There's still so much to learn. Juno is just one piece of the puzzle. Let's zoom out and take a look at other ongoing planetary exploration missions. We have spacecraft studying Mars, asteroids, and even the outer reaches of our solar system. Mars remains a major focus of exploration. NASA's Perseverance rover is currently exploring Jezero Crater, a site believed to have once been a lake. Its primary goal is to search for signs of past microbial life and collect samples that will eventually be returned to Earth for further analysis. Curiosity rover found evidence that ancient Mars had the right chemical ingredients and conditions to support microbial life. It found evidence of liquid water and other chemical building blocks. Beyond the inner solar system, NASA's New Horizons spacecraft, which famously flew past Pluto, is now exploring the Kuiper Belt. It has already studied several Kuiper Belt objects, giving us a glimpse into this icy realm. What does the future hold? There are many exciting missions in development. Europa Clipper. This NASA mission will repeatedly fly by Jupiter's moon Europa, which is believed to harbour a subsurface ocean, searching for signs of habitability. JUICE, Jupiter, Icy Moons Explorer. The European Space Agency's JUICE mission will also explore Jupiter's icy moons, focusing on Europa, Ganymede, and Callisto. Da Vinci will plunge through Venus's harsh atmosphere to explore its composition and understand how it became so different from Earth. Of course, exploring other planets is not easy. Spacecraft have to endure extreme temperatures, radiation, and long travel times. Communication delays can be significant, and the risk of failure is always present. Building spacecraft that can withstand these conditions requires incredible engineering and ingenuity. Despite the challenges, the benefits of planetary exploration are immense. It expands our knowledge of the universe, inspires future generations of scientists and engineers, and drives technological innovation that has applications here on Earth. Plus, it gives us a new perspective on our own planet and our place in the cosmos. From the first beeps of Sputnik to the stunning images sent back by Perseverance, space probes have revolutionized our understanding of the universe. They have allowed us to explore worlds beyond our own, search for life, and push the boundaries of human knowledge. Space exploration is not just about scientific discovery. It's also about inspiring future generations, fostering innovation, and addressing some of humanity's greatest challenges. The future of space probes is bright. With new technologies and ambitious missions on the horizon, we can expect even more groundbreaking discoveries in the years to come. The journey of robotic exploration is far from over. It's just beginning. If you enjoyed this video, please like, share, and subscribe. Let us know in the comments what your favorite space probe mission is and what you'd like to see us cover in future videos. Thank you for joining us on this cosmic journey.